Okay, we're going to do the final topic in this course, and it is soil strength. So there are, well, first the concept is this. When we talk about soil strength, we're talking about soil shear strength. So in other words, it contrasts with steel, for instance. If you talk about steel strength, you're talking about tensile strength. You don't mention it. You say, what's the strength of your steel? Well, automatically you know that when you talk about strength of steel, you're talking about the tensile strength of the steel. At the same time, when we talk about strength of the soil, without saying it, we are talking about the shear strength of the steel. And there are two kinds of shear strength: drained and undrained. Now, we don't have that issue with steel, concrete, wood, whatever. This is something that is unique to soils: drained strength or undrained strength. And what we find is that there are two kinds of loading in situ. We have drained loading and we have undrained loading. So we have drained and undrained strength. We have drained and undrained loading. Again, something that we don't have in structures. We will talk about whether we're loading the soil drained or undrained. And the concept is that if we have drained loading in situ in the field, we use the drain strength in our analysis. And if we have undrained loading in the field, we use the undrained strength in our analysis. And in a nutshell, drained loading is slow, undrained loading is fast. So the rate of loading is important. Again, this is not really something that comes into play with structures. It's something unique to soils. Now, the way it works is in the lab, when we run a strength test, if we apply the load rapidly or fast, we are running an undrained test. And at failure, we get the undrained soil shear strength. If we apply the load slowly in the lab, we're running a drained test, and at failure, we get the drained soil shear strength. So, in other words, we do this in the lab as well as in the field. We can load this soil rapidly, or we could load it slowly. Now, why are we interested in the soil shear strength? Well, for instance, for a structure, we build our structure like this. If the soil is not strong enough, then we end up with this situation. Literally, the building can tip over. And what we get is a shear plane at the base. So in other words, we have shearing resistance of the soil, and in other words, we can get a failure. For instance, if we take moments about this point approximately, and we have the weight of our structure, we have the shearing resistance of the soil, and what we see is the weight of the structure. If the moment caused by the weight of the structure is greater than the moment caused by the shear resistance, then we can get a failure. The classic picture of this is this right here, where we have what's called a bearing capacity failure. And we can't see it, but underneath here is a shear plane. You can see the soil piled up on this side. So that's your classic your classic bearing capacity failure. Now, I want to say something about the concept that we have to get familiar with and why we use the term drained and undrained. So, it's a new concept, and that concept is that shear stress can cause an excess pore pressure. We've talked about excess pore pressure and how it's generated in our settlement problems, but what we're going to find is that that excess pore pressure can also be caused by shear. The concept is this, is suppose I have this soil here and I am going to create for instance, a shear plane in here. And how do I create that shear plane? Well, in a sense, one way to look at it is that, I'm getting pushed one way at the top, a different way at the bottom, for instance, and in between I get a shear failure plane. And in essence, that's what's taking place down here. I have my shear plane is right in there. So what's going on there? Well, let's assume for the time being that my soil particles are in this state where I have contact points of the soil, and in between I have water. So we're talking about a saturated soil at the moment. And what happens is that when movement takes place, that the soil particles can then fall into the void. So in other words, that void becomes much smaller. That void becomes much smaller because the particles fall into, as movement takes place, the particles fall into the gaps. And what happens is that if the particles are falling into those gaps, then you're going to get the water in the voids get squeezed, and we get an increase in the excess pore pressure. And notice, what does that mean? Shear stress causes the excess pore pressure. So, new concept, you need to know that the shear stress can produce an excess pore pressure. Then the issue with why we use this undrained and drained terms refers to how quickly that excess pore pressure will dissipate. So in other words, the way to what we can see is if the soil is a sand or gravel, if these soil particles, for instance, are sand or gravel, sort of as I shown there, that excess pore pressure will be created, but it will dissipate very quickly because the water moves very quickly in sand or gravel. Whereas if it is a clay or a silt, the excess pore pressure does not dissipate very quickly because water does not move very easily in clay or silt. So that is the concept, and that is why we end up asking the question, how fast is fast? And in other words, we said if we load it quickly, it's an undrained loading. If we load it slowly, it's a drained loading. Well, the answer for how fast is fast is that it depends on the soil type, and it depends on how fast excess pore pressures can dissipate. So we've generated these excess pore pressures. How quickly do they dissipate? And just as we said, if it's sand or gravel, well, except for earthquakes, we use drained loading and drained strength. Why? So in other words, drained being that the excess pore pressures have dissipated. Well, in general, if we're building a structure, for instance, we cannot building a structure. We cannot normally load the sand and gravel fast enough in the field to make it fast. In other words, like I said, it goes back to our picture here. We're creating the load W. Well, how long does it take us to create that load? Well, it takes us a long time to build that structure. And so in the process of building the structure, as this W increases due to the weight of the structure that we build, up and up and up, for instance, then the excess pore pressure that is generated along that shear plane, that will pretty much dissipate during the construction process, so we never really get large excess pore pressures with sand and gravel due to the building of a structure, because we just can't build the structure fast enough. The pore pressures dissipate faster than we can build it. The exception, or a loading, when we have an earthquake loading, that's a different story. So in other words, if our shear stresses are caused by an earthquake, and here I've shown, approximately what happens when we have an earthquake, what happens. The base rock moves, for instance, back and forth horizontally and creates a seismic wave that travels upward through the soil. And you can see sort of, the seismic wave, the soil is going that way, it's going that way. You can see the shear stresses generated with this seismic wave. And so we get a lot of shear stresses in here. And what do we know? Well, a cycle, one cycle of an earthquake load, maybe 1 second. So one cycle of the wave is 1 second. That's faster than the excess pore pressures can dissipate. So typically when we're looking at like seismic waves, we will say that the sand or gravel could be loaded undrained, and we get excess pore pressures simply because the seismic waves have such a short cycle. We can't get full dissipation within 1 second in typical sand or gravel soil. So that's why I say, except for earthquakes, we use drained loading. So in other words, if we have an earthquake, we would consider that undrained loading in sand. Everything else is drained loading, so we don't have to think about too much with sand or gravel. We're just going to assume that we have drained loading and used drained strengths in our analyses. And that's what we're going to do for this class. We are not going to consider the earthquake loading situation. On the other hand, for clay and silt, for normal construction, we would use undrained loading and undrained strength for immediately after construction. So in other words, let's just say it takes us a couple years to build our structure. Well, a lot of times that is, a couple years is not enough time for all the excess pore pressures to dissipate. We've been looking at the dissipation of excess pore pressures in our settlement problems. And what are we looking at? We're looking at, 5, 10, 20 years for the excess pore pressures to be completely dissipated. So what we find is that a lot of times during our construction process in clay and silt, we are actually doing undrained loading because we're building it faster. We're building our structure faster than the pore pressures can dissipate. And so we use the undrained strength in our analyses. But now that is we're going to end up for clay and silt. We're going to consider the situation immediately after construction, but we're also going to consider a long time after construction. In other words, we build our building, but it's going to sit there for 50 years, most of the time, because we want our building to last for a long time. So what we have to do two analyses for clay and silt. One, we have to do the undrained loading and undrained strength, because the building is going to be there immediately after the construction, but then we want our building to remain for a long time, so we also have to do use drain strength, drain loading for a long time after construction. So we have to do two analyses. So I recommend this acronym that is easy for us to remember. EDS, EDS, TOUGH. EDS, TOUGH. EDS, what does that stand for? Effective, drained, slow. So that reminds us that when the loading is slow, we have drained loading, and we use the drain strength, and we use effective stresses in our analyses. We'll see. So effective stresses, drained, EDS, effective, drain, slow. Those three go together. That tells us about the speed is slow. We use drain strengths. We use effective stresses. That's how we do our analyses. TOUGH, what does that stand for? Total undrained fast. And so that means our loading is fast. We use undrained strengths. We use total stresses in our analyses. So EDS, TOUGH. It's just a handy way to, you remember that acronym, and it will solve some problems for you when you start doing your analyses. Okay, if we look at a test in the lab called a direct shear test, DS, or shear box test, we have one of these devices in our lab. It looks like this. We have, this is the box here. It has a split, and what we do is we apply a vertical load and we keep it constant, and then we increase F until we get failure. And what happens as we increase F, we create a shear plane here, and what we do is we plot F versus delta. The delta is the deformation. And what happens is it looks like a stress strain curve when we do it. We plot F, we plot delta, and what happens as we increase F, we increase delta. Increase F, we increase delta. Increase F, we increase delta. Now what happens is eventually we keep trying to increase F, and it reaches a peak, and we start getting large delta. So, like I say, it looks like a stress strain curve. Now, we have to remember we keep the P constant. This is, again, a little bit different. It looks like a stress strain curve, but we don't have this P issue when we run a tensile stress in steel, for instance. We don't have this, but in soil mechanics we do. So in other words, we choose a P, we keep it constant, and we get a certain F max. Now, if we chose a different P, we would get a different F max. So this is a little bit more detail of the box here. What have we done? We apply this P here, and it has a top cap, and then that's what the device looks like a little more closely. In plan view, what do we have? We have a cross-sectional area. This is the box. Again, it's the box, and then there is our F in plan view. So this is our raw test result. Again, the F delta, that's what we measure in the lab, and we plot it. What do? We want to convert it to stresses. So the shear stress tau is F over the cross-sectional area. So what we're going to call tau FF, tau at failure on the failure plane, is the F max over the cross-sectional area. We also have a sigma. Sigma is P over the cross-sectional area. And we don't change P during the test. So our sigma FF, in other words, the sigma at failure on the failure plane, is P over the cross-sectional area. And as I say, FF is at failure on the failure shear plane. And so in other words, we convert the F delta curve for a particular given P to a tau gamma. Now gamma is not density, gamma is shear strain, if you remember shear strain. And well, so we get a shear stress shear strain curve. So just watch out when I draw that gamma there. It's not density, it's shear strain. And then we have that tau FF for a given sigma FF. So we choose the P, which gives us the sigma, which gives us the sigma FF, and that gives us the, and then when we run the test, we get the tau FF. Now, one of the things we're going to note for sand and gravel, the lab test is a drained test because the pore pressures dissipate so quickly. So, in other words, we're not going to run it so quickly in the lab that we generate excess pore pressures. We just get UXS equals 0 because the pore pressures dissipate so quickly. Now, what we find is that we can run, in other words, if I change my sigma FF and that means I change my tau FF, I can run a series of these at different sigmas. And now note, because the excess pore pressure is 0, sigma FF and sigma prime FF are the same. So in other words, I'm going to, well, this sigma FF is going to be a sigma prime FF. This tau FF is right there. So I can take the results of this test, for instance, sigma FF, tau FF, make it a sigma prime FF and a tau FF, and plot that point on this curve here. And what happens is that for sand and gravel, I can create a failure envelope. I take that point, I take the origin, and I draw a line, and I create a failure envelope. So notice the axes here, sigma prime and tau, and I create that failure envelope, and what do we find? We find that any stress below that is our no failure region. Any stress above that would be our failure region. So in other words, in the field, in situ, I can look at my stresses that I create and plot it on this particular plot, and I can determine whether or not I get failure. If I'm below the envelope, I have no failure. If I'm above the envelope, I get failure. And we use the symbol phi prime, the friction angle, or the angle of internal friction, that defines the failure envelope. Now, if you remember, our basic friction equation is what? F equals mu n. Well, in soils, what do we find is that the way that it works is that the mu that we always talk about, you can get it by it's the tangent of the friction angle. So we can get the coefficient of friction for our soil, for our sand or gravel soil, simply by taking the tangent of the friction angle. And so, as I said here, since the pore pressure is 0, the excess pore pressure is 0, the pore pressure is 0, we find that sigma prime is equal to sigma minus u, sigma prime equals sigma. So our sigma prime FF is simply our sigma FF, which is P over cross-sectional area. And then, okay, this is an important page, so I want to finish with this. Know this page. This page shows the representation of soil strength for different soils and conditions, you should memorize the 3 plots. All right, let me describe the 3 plots. We just went through sand and gravel drained. So this is for all cases on sand except for earthquakes, for instance. And we just went through it. We plot tau, sigma prime, and the failure envelope that we get is defined by phi prime. And notice that the failure envelope goes through the origin. For clay and silt drained, again, in other words, we run this, in the lab we run the test very slowly. We get clay and silt and drained envelope. It's a little bit different. We get a C prime and a phi prime. So in other words, the failure envelope does not go through the origin. It goes like that. So we get C prime and phi prime for clay and silt. That defines the failure envelope. And then what we will find is if we have clay and silt undrained, in other words, if I run the test fast in the lab, then I get a different failure envelope. It looks like this. It's horizontal. And first of all, I'm going to notice that I have sigma, not sigma prime. So in other words, up here is sigma prime, up there is sigma prime, but down here it's sigma. So, and that is going to be important for us. Because why? Because for undrained loading, which is fast, where are we? Total undrained fast. So that T total means sigma, not sigma prime. That's total stress. Whereas effective drain slow, which are these 2 cases, the E effective means sigma prime. That's the way we define the envelope. Okay, so you need to know this page. And here's the intercept here is called C cohesion or SU undrained shear strength. 2 different names for it. Either one is acceptable. And notice it is horizontal. Here I need C prime and phi prime. Here I just need phi prime to define these envelopes, these failure envelopes. So know this page. Okay, I'll stop there.